Hello everyone, welcome back. Another NatPhi chemistry tutorial. Last time I was talking about how you write down the electron arrangement for atoms like carbon, oxygen, sodium. Carbon being 2,4, oxygen being 2,6, sodium being 2,8,1. So that's 2 electrons in the first shell, okay? And 4 electrons in the second shell, okay? And that's the third shell. Okay, 2 electrons in the first shell, 4 in the second shell. So when you have, for a single hydrogen atom, I showed it was one positive with an electron in orbit around it, okay? For a sodium atom, you have a positive nucleus, okay? And then you have 2 electrons in the first shell. Then you have a second shell where you have 8, so you have 1, 2, 3, 4, 5, 6, 7, 8, okay? And then the third shell you have 1, so you do another, and you have a single, put it here, okay? So that's the arrangement of electrons in the sodium. There's more than one charge. It's written as 1 positive. This actually has 11 protons. Nucleus. Okay, so 2 electrons in the inner shell, 8 electrons in the second shell, 1 electron in the third shell. Okay. So the periodic table is when you write the sodium, you actually normally write it in this way. 23 is the mass, okay, and the atomic number, okay. We don't need that. Atomic number. Carbon is 12, 6, okay. Oxygen is 16, 8, okay. So that's the mass, that's the atomic number, okay. Okay. So all atoms, the basic atom contains, there should be a 6, 8, 11 protons, okay. There's there is another kind of way of atoms can exist. Another way okay, and that's what you call isotopes. Okay, so isotopes basically have same atomic number, but a different mass number, okay? So what this means is that they are different by 1 neutron. By the number Okay, so you have, okay, so for example, carbon normally is 12, 6, okay? But an isotope is carbon 6 atomic number, but 13, okay? So there's one more neutron, okay? So in this case, this is number of protons equals 6, number of neutrons equals 6, and the mass number equals 12. Here, protons equals 6, neutrons equals 7, mass number equals 13, okay? Oxygen, so you have 16, 8, and an isotope would be oxygen, it would be 8, okay? But that'd be 17 because it's got one more neutron, okay? So yeah, and you can obviously, you see here, if you take the mass minus the number of protons will equal number of neutrons, okay? So 13 minus 6 equals 7, okay? Hope that's clear. So another good example is copper, okay? Copper, which is symbol Cu, okay? So copper has mass 63, okay? And there's also, you got copper with mass 65, okay? This says 29 protons, okay? And this is 29 protons, okay? But one's got, this has got 2 more neutrons. Okay, so you've got periodic table, copper has mass 63.5, number of protons is only 29, atomic number 29, mass number 63, it's actually 63.5, but am I right, 63? We normally actually write 64 because it's, you round up. Should really have written that as 64.29. Okay, so there's 2 isotopes of copper. Okay, another, so this is the definition of an isotope. When you get elements existing where you get the same element but they're 2 different masses, it's because one of them has got more neutrons. And you find sometimes when you're radio dating, when you take archaeology or rock samples, you can work out how old things are by looking at the isotopes of an element like oxygen or carbon, okay? And we know the half-lives of the atoms, so you can work out how old, you can work out the ratio of, say, carbon 12 to carbon 13 or oxygen 16 to oxygen 17 in materials which are very old, rocks or archaeology, and therefore you can work out how old something is because you know the half-life by the ratio of these 2. So Another quick mention, ions, okay. Atoms can lose or gain electrons, okay. So an ion is formed if you have a magnesium atom and you okay, this is an ion, okay, magnesium 2 plus 2 electrons. This means it's lost, okay, so this is 2 electrons that have been lost. So these electrons sometimes students think this means the magnesium ion plus the electrons, so this is the atom. No, that is the atom, okay? The atom. This is the ion, and these are 2 electrons which have been lost from the atom, okay? And this is an example of oxidation, okay? This is actually oxidation. Okay, so that's one example of ions forming. Or you could have sodium okay, again, electron has been lost. That's the ion and the atom. Okay, so sodium loses 1 electron to become positively charged, and it has 1 electron comes off it, okay? So it loses the electron, becomes positively charged, okay? Another example of ions forming is take chlorine atom plus an electron, okay? So in this case, that's an atom. The chlorine gains an electron to become an ion, okay? So this is actually reduction. This is oxidation reduction, which is later in the syllabus, but one way of writing oxidation reduction is you can say that reduction is gain of electrons. Reduction is the gain of electrons, which that equals Reg. Reduction is gain, okay? And oxidation loss of. Okay, and that equals oil. I was taught this a long time ago, although not everybody it seems has heard of it, but so you can write oxidation and reduction as oil rig. So oxidation is loss, reduction is gain. It means, as I said, oxidation, this is oxidation, okay? Oxidation, the sodium loses an electron, okay? So that's loss. Reduction is gain of electron, the chlorine gains an electron. You could also write bromine plus electron becomes bromine, negative, okay? So this is reduction, okay? So this is oil rig. This is a simple way to remember oxidation is loss, reduction is gain. But it's just an amusing way to say it, oil rig. Okay. Unlike the rest of the atoms, the noble gases and ions, okay? So these are stable and unreactive. Okay? Helium, periodic table, helium, neon, these are very faded. It's an old one. Krypton, argon, okay? Xenon, I think. So these are helium, neon, krypton, argon, xenon. Helium, neon, krypton, okay? Argon. So these are unreactive and very stable. They will never form ions, okay? Okay, and it's because they have a full outer shell of electrons. Okay, so for example, helium is 910 to 8. Okay, neon is 2, 8, 18. Okay, and krypton is 2, 8, 18, 32. Okay, so these are basically the second shell. I said previous lecture, the first shell has a maximum of 2, second shell has a maximum of 8, third shell, these are the maximums, okay? That has a maximum of 18, and the fourth shell is a maximum of 32. So these cannot gain electrons and they cannot lose, but they're completely full, okay? So those are noble gases and ions. I will quickly go over bonding structure and properties, okay? So water molecule is a simplified way of writing is like this. That's the oxygen plus hydrogen, okay? These are the atoms of water are joined by covalent bonds. Okay? The reason it's called covalent, the word valent actually refers to the valence electrons, which are outer shell electrons, okay? Which are the outer shell okay, and because there's two atoms they're called covalent because they both line up basically. So covalent means they two atom bonding electrons line up. Okay, that's where the name comes from. Okay, so yeah, in the covalent bond you get sharing of electrons. Okay, I haven't actually said that yet, but so you get a sharing of electrons, pair, between two non-metal okay, that's what covalent bonding is. The sharing of a pair of electrons between the sharing of a pair of electrons between two non-metal atoms. Okay, that is a covalent bond. So you have two positive nuclei. Start again. And you have two electrons shared, okay? And two electrons shared, okay? So this could actually be, this is a hydrogen molecule. That's a hydrogen molecule. I think I'll actually maybe could carry on, maybe do a bit more. So with oxygen, you have that should be more in the middle. Okay, so you have oxygen. We said was 2, 6, didn't we? So you have they share each. This is actually a different kind of. This is a double bonded. Maybe I started actually going with fluorine because it's single bonded. So you got okay. We know that fluorine is what was it? It's 17, 9, okay? Sorry, that's wrong. Fluorine is 19 mass and 9 protons. Okay, so there's 2 in the inner shell and 7 in the outer shell, okay? So you draw them as 1, 2, 3, 4, 5, 6, 7, okay? It doesn't matter whether you do circles or crosses, it's the same effect. You're trying to show probably actually also do these differently. Actually, I'll do them as circles. Okay? There wasn't a reason I actually started filling them in like 1, 2, 3, 4, 5, 6, 7, but that's high grade knowledge, advanced high knowledge. So I've represented the electrons of this fluorine atom by circles and electrons of this fluorine atom by crosses. These refer to these electrons, okay, the second shell electrons, okay? So